Good day, Grade 12s. I'm Taryn Roberts, and welcome to STEM in Action's Boost series. Today we are looking at the topic Electrodynamics. So electrodynamics is divided into two sections in your curriculum. The one deals with electrical machines, both generators and motors, and the other section talks about alternating current. In part 1, we will look at AC and DC generators as examples of electrical machines. But of course, let's consider the pre-knowledge required to understand electrical machines. So in grade 11, we looked at a current carrying conductor, and we learned that a current carrying conductor generates a magnetic field. So if we have I, current, we have a magnetic field around that wire. We use the right-hand wire rule to determine the direction of that magnetic field. So right hand, we take our right hand and we'll use our fingers and our thumbs. So let's see how that works. So over there I've got a wire, and we take our thumb, which points in the direction of the current from positive to negative, and our fingers would curl in the direction of the magnetic field. So let's have a look at the example or the animation we have over there. We have a wire, and when it doesn't carry current, we don't have any deflection of the compass on top or below the wire. The minute we connect that wire to a power source, we have current, and the minute that wire carries current, there's an associated magnetic field around that wire. The thumb points upward, and the fingers curl in the direction of the magnetic field. We use the right-hand wire rule, and we can see that associated magnetic field around that wire by the deflection of the compass needle pointing to north. In the case of a solenoid, we now take that same wire, and all we do is we loop or we curl it to form a solenoid. We once again have current, and around that solenoid we will therefore have a magnetic field. We use the right-hand solenoid rule, in this case, to determine the direction of the magnetic field. But now we're going to use our right hand slightly differently. In this case, we're going to take our fingers and we're going to point them in the direction of the current. So if we look at the left-hand side, the magnetic field there, we can see it's going from positive to negative. And so if I take my fingers like this, and I point it and I curl it around, my thumb points down. So my fingers are pointing in the direction or curling in the direction of the current, and my thumb points down naturally as I use the right-hand solenoid rule, and it points in the direction of the magnetic field. It points to the North Pole. We've also learned that a current carrying conductor moving in a magnetic field induces an EMF. This is quite key for the understanding of the rest of generators, motors, as well as alternating current. There's a change in magnetic flux linkage. So when we've got a current carrying conductor moving in a magnetic field, there's a change in magnetic flux linkage which induces an EMF. The word induces means to bring about. So an EMF is brought about when we have two criteria. One, we've got current in a conductor, and that conductor needs to be moving, or there needs to be a link of magnetic flux changing between the magnetic field and the current in that conductor. Once we have those two criteria checked, we then have EMF, which is induced. So we can allow, or we can get the magnetic flux linkage to change relative to the current in the conductor and the magnetic field, and we can do that doing two things. One, we could take the conductor and move it in and out of the magnetic field. That would give us a change in magnetic field flux linkage. Or we could keep the conductor stationary and move the magnet over the conductor. In both these cases, we have a change in magnetic flux linkage which would induce an EMF in the circuit. This brings us to Faraday's law. And Faraday's law says that the EMF induced around a single loop of conductor is proportional to the rate of change of magnetic flux through the area of the loop. Mathematically, this can be written as EMF, or induced EMF, equals minus N delta phi over delta T, where phi is our magnetic flux, and it's given in the equation of B multiplied by the area times cos theta. And B is our symbol for magnetic field. And of course, area is the area of the loop of the conductor. And that negative indicates that the induced EMF opposes the change in magnetic flux. So that's Faraday's law. Now we are ready to cover generators. So we've got a generator. I'm hoping that image brings about memories, hopefully positive ones. I always think of load shedding when I see generators. But it's important to realize that a generator is a device that converts mechanical energy to electrical energy. So we do not have a power source. We have to bring about an EMF or induce an EMF. It is based on the principle or Faraday's law of electromagnetic induction. And for generators, we can determine the direction of the induced EMF using Fleming's right-hand rule. So if we consider electromagnetic induction and generators, there we've got a generator. How do we know that we've got a generator? Number one, we've got a coil, we've got a conductor. And number two, there is motion. It is moving in a magnetic field. The minute we've got a current carrying conductor moving in a magnetic field, we've got a change in magnetic flux linkage. That induces an EMF. How do I know that there's an EMF induced? Because this brings about current, which allows that little light bulb to shine over there. Nowhere in that animation do we see a power source. So we know that this is not a motor. We know that it is a system or a device which is generating electrical energy through the use or converting mechanical energy. So electromagnetic induction and generators, it is based on a coil rotating in a magnetic field. The coil is attached to an external circuit. That coil, you can see it's attached to the light bulb, and it is mechanically turned. That brings about the change in magnetic flux linkage. And of course, once all those are in check, an EMF is induced. And the minute we've got an EMF induced or voltage, we have current which is generated. Now it's important. The direction of that current generated can either be alternating current, then we have an AC generator. Or if the direction is direct current, we have a DC generator. So this is quite a principle to understand, and it's key to linking these concepts and ideas into understanding AC and DC generators. So let's look at Fleming's right-hand rule for generators a little bit closer. So we've said when we've got a conductor in a magnetic field and they move relative to each other, we have an induced EMF. We are able to determine the direction of that induced EMF by using Fleming's right-hand rule. Of course, we need to use our right hand. Now, we're going to use 3 digits on that right hand. The thumb, the first finger, and the second finger. Important, they need to be at right angles to each other. So there are many associations for this Fleming's right-hand rule. They call it the FBI gun. So not a gun that we like to see, but an FBI gun. Force, magnetic field, the symbol for magnetic field we learned in Faraday's law to be B. And current, the symbol for current is capital I. So FBI. I like to be a bit more family orientated, so I've got my thumb, which gives me the direction of the force. Father. Then my first finger gives me the direction of the magnetic field. Mother. And then of course they get together and they have a child. That gives me the direction of the current. How you find associations to remember the orientation of the fingers and in which direction they point is entirely up to you. But I've given you FBI and I've given you father, mother, and child. Important that they have to be at right angles to each other. So if I take my right hand and my thumb gives me the direction of the force or the rotation, how am I rotating the conductor? And my first finger gives me the direction of the magnetic field from north to south. My second finger will be the direction of the induced EMF or the current that is being generated by this device. So we use Fleming's right-hand rule, there's the orientation, and that's a reminder. Father, mother, and child. Force or rotation, magnetic field, and current, and they're all at right angles to each other. How do I remember this? There's a right hand and a left hand, and trust me, this becomes key, especially in part 2 when we cover motors. So I have a little recall tip. I say in a test or exam, we always want to generate the right answers. So for generators, we use the right-hand Fleming rule. We've been looking at Fleming's law of electromagnetic induction, which generators are based on. So it is important to understand what are the components of a generator. So in this segment, we will consider the components of an AC generator as well as a DC generator. You need to know these components, and you also need to know which components are found in AC that are not found in DC generators, and vice versa. So let's take a look. Very important. The key difference between an AC generator and a DC generator is that an AC generator has 2 slip rings. There they are. 1 slip ring, 2 slip ring. How do I remember it? Well, I encourage you to bring yourself into your learning. So I'm going to share my association with how to remember slip rings, but I do encourage you to bring yourself into your learning. So if you can find an exciting association, please text our office. You know it's STEM admin, and let us know your creative ways of remembering certain facts and ideas. So on the topic of AC generators and the component of slip ring commutator, how do we remember it? There are 2 of them, and on a wedding day, a husband and a wife, they slip a ring on each finger. So there's 2 rings, 2 slip rings, okay? Those rings are connected to what we call brushes. And there they are. There's 1 brush, and there's the second brush. And if I consider the wedding cake over there, the rings signify 2 slip rings. You're never going to find a husband marrying himself. So we need to have 2 people in the marriage. And then if we have wedding cake and they get all crumbs on the floor, we need a brush to sweep that up. So we've got 2 brushes. There is our coil. So in our generator, we need a coil. So there it is. Another term for coil is the armature. And each arm or side of the coil connects to 1 slip ring, and there's the other connecting to the other slip ring. And they're connected to the external circuit via brushes over there. This coil is in a magnetic field, so we've got 2 permanent magnets there, and we rotate it mechanically. There's someone who's going to take the handle and rotate that armature or coil mechanically. That is how we get the mechanical energy, creating a change in magnetic flux linkage between the conductor and the magnetic field, and this generates an EMF. And if that EMF is induced, we will get this little light bulb there in our external circuit, or in this case it's our load, that will start glowing. And that gives us evidence that mechanical energy has been converted into electrical energy. Important to note, for an AC generator, the electricity or the current that is generated, it changes direction every half revolution, or every 180 degrees it changes its direction. Hence it is called alternating current, and hence we have an AC generator. There's another top view of the AC generator. We've got, for all generators, we need a coil in a magnetic field. And in this case, I know that it's AC because I've got the 2 rings that they slip onto each other's fingers. We've got the brushes and we've got our external load. That's just showing you the generator from top view. Let us go and have a look at an animation which shows the operation of an AC generator, and will also be able to show us how the current changes direction every 180 degrees. Right, grade 12s. So let's have a look at this animation of a generator. Let us first determine if this is a generator or not. So let's go and do the checks. Well, in my contraption or my device or apparatus or setup over there, nowhere do I see a power source, which means I do not have a start or a start-up of electrical input or electrical energy. So I do, however, see a voltmeter, and that voltmeter would pick up an EMF that's generated. So chances are this is a generator. Let's go look further and see what kind of generator is it. An AC generator or a DC generator. And beautifully over there, I can see those two wedding rings. Grade 12s, please in your exams, don't go and say it's an AC generator because there are two wedding rings there. Okay? They are slip rings. The wedding rings association is just a tip for you to recall the actual physics content in a test or an exam. But yes, you're right, we do see two little slip rings over there, and the mere fact that I've got two slip rings tells me we're dealing with AC. Is this a generator? Yes, because I do not have a power source, but I have a voltmeter which would read an induced EMF. Then furthermore, I've got my armature or my coil, and it's placed in a magnetic field. We're going to rotate that coil, and the mere fact that we've got a coil being rotated or mechanically moved in a magnetic field will induce an EMF. And then we've got an axis over here. On a y-axis, we're measuring voltage, and our x-axis, our independent variable, is time. So we're looking at the induced EMF over time for this AC generator. So have a look. You can see as that armature rotates within a magnetic field, we've got an induced EMF which generates current. And you can also see, let's have a look at it again. As it rotates, you can see that that induced EMF generates a current, and that current changes direction every 180 degrees. We can see for the first 180, we've got a positive maximum voltage, and then the second set of the cycle, we've got a negative maximum voltage. That negative maximum voltage doesn't mean that we have a minimum voltage. No, we just have a voltage in the opposite direction. So for every 180 degrees, or every half revolution, the direction of this induced current changes every 180. I want to bring your attention to the orientation of this coil. So currently, that coil is in a horizontal position. I want you to look at the frame of the coil, and I'm also going to talk about the area of the coil. All right? So as we go and we have a look, we can have a look at the vertical position. That's a beautiful spot for me to stop there. In that position, if I look at my graph, I can see that the maximum voltage is reached when the orientation of the coil is of such a nature that the coil is in a vertical position. The coil frame is cutting the magnetic field, and if I take the frame or the area of the coil and I draw a normal to it, it's perpendicular to the magnetic field. So when the area of the coil is perpendicular to the magnetic field, we will generate a maximum EMF. And of course, when the coil is in the horizontal position, if we draw a normal to the area of that coil, it is parallel to the magnetic field. When they are parallel to the magnetic field, you can see we have zero induced EMF. So we do not have a current that's generated. It is important for you to know when the EMF that's induced, when is it a maximum and when is it a minimum in relation to the orientation either of the frame of the coil or the area of the coil. This brings us to DC generators. Of course, in the same way that we need to know the components of an AC generator, we need to know which components make up a DC generator. So you can acknowledge that that looks pretty similar to the AC generator, but let's see how they differ. Number one, where we used to have two slip rings, we now have one split ring commutator. There we have it, a split ring commutator. Now grade 12s, I love food, if you haven't figured that out yet. And the best way for me to remember what's the difference between slip rings and a split ring commutator is to think about a hamburger. But unfortunately, this hamburger does not have a patty. So we've got two hamburger rolls. There's my ring that's been split. So we've got the upper half and the lower half, and this rotates. How do they rotate? They rotate between two brushes. So the brushes remain stationary while the split rings rotate over there. So of course, in the same way that we had brushes in the AC generator, we also have them in the DC generator. And it's those brushes that connect the coil to the split ring commutator, and that links to the external circuit over there. And as I said, we've got a coil in a magnetic field. Those are common to both AC and DC generators. So as this coil rotates in the magnetic field, two things are checked. Coil rotating in a magnetic field, this induces EMF. In the case of a DC generator, the current does not change direction. Thus, the generator generates direct current. The current does not change. It stays directly in the same direction, and we now have a DC generator. Top view again, we can see the common components. We need to have a coil, an armature that needs to freely rotate in a magnetic field. We have an external load. Previously it was a light bulb. Now we can see that that light bulb is represented by the symbol for a resistor. We've got our brushes, which are still common to generators. And the distinct difference is that a DC generator has a split ring commutator, while AC generators have two slip rings. And there we can see the top view, the split ring commutator, hamburger roll with no patty. Let's consider an animation which hopefully will show how the DC current generated through a DC generator, how that affects the maximum induced EMF and the minimum EMF induced by looking at the orientation of the coil. At first glance, you will think, what is going on? It's the exact same animation as we saw 2 seconds ago. However, there are slight differences. Let's go and look even closer. Number one, I need to decide, is this a generator? Let's go and see. So the device I have here, it lends me to believe that it is a generator because I see an armature, I see a magnetic field. But the deciding factor, or the clear factor here, is that current is being generated. There is no electrical input. I've got a voltmeter which is going to measure the induced EMF, which is a result of mechanical energy being converted to electrical energy. So yes, I have a generator. Is it an AC generator? Well, go and see. Are there 2 little rings here? Absolutely not. Do I see a hamburger roll without a patty? Absolutely yes. I can see the split ring commutator, and you can beautifully see the top and the bottom and the gap in the middle. They are connected by a brush on the top and a brush at the bottom, and that connects to the coil or the armature in the circuit. That coil is sandwiched between magnets. So we've got, as that coil rotates, we are having a change in magnetic flux linkage brought between the mechanical rotation of the coil, and this induces an EMF. And if you can remember, we can determine the direction of that induced EMF. What do? We generate the right answer, because generators use right hand's Fleming rule to determine the direction of that induced current. So let's go and see how this voltage versus time graph looks, how differently it looks compared to an AC generator. So let's play this animation, and I want you to look at the orientation of the coil as it rotates in the magnetic field. There we've got the voltage time graph, and it definitely looks different. That graph shows that the voltage stays positive in this case throughout the rotation. We do not have the graph forming a sine graph. We have the graph staying above the x-axis. That graph could also only show us below the x-axis. Don't think it always has to be positive. But the point is, the graph generates a shape which shows that the direction of the induced EMF does not change through the rotation of the coil. So if we have a look at this orientation over here, we've got our coil in a vertical position. If we have a look at our graph, it shows in that position the voltage or the EMF induced is actually a maximum. So let's have a look at the orientation of the coil in 2 ways. If we look at the frame of the coil, we can see the coil is in a vertical position. But if we look at the area of the coil and we draw a normal perpendicular to the area of the coil, that normal cuts the magnetic field perpendicularly. In this orientation, the induced EMF will be a maximum. If we now continue rotating this coil to a horizontal position, so now we've got the coil in a horizontal position, the normal to the area is parallel to the magnetic field, and guess what? In that orientation, the induced EMF is 0. I want you to have a look. There's 180 degrees, 360, that would form one cycle. And in that one cycle, we did not have a change in direction. The voltage remained positive. So we have a DC generator which is displayed in this animation. It's quite important, so I want to show you another animation which describes when is the EMF induced a maximum and when is it a minimum. So in case you missed it, when the magnets were in a vertical position, we're now looking at it, which is most common where the magnets are in a horizontal position. And let's see what we discussed, if it still applies in this situation. If you have a look at the setup over here, we have, again, magnets, we've got a coil, and we have got a graph which is going to show the induced EMF over time. We've got a device over here. In this case, it's not a voltmeter, but it is a galvanometer. You might have remembered galvanometer when we covered the section of galvanic cells in electrochemistry. And in the same case, a galvanometer will deflect in the direction of potential difference. So if we have a look here, and let's play this, it's quite slow, so we can see how this coil is rotating. And let's have a look in our graph. It's approaching the horizontal position, and I just want to stop it right there. So let's compare. If I look at my graph, if I look at my coil, the coil is in the horizontal position. It's almost slicing the magnetic field. In that position, if I draw normal to the area of the coil, that normal will be perpendicular to the magnetic field. In this orientation, when the normal is perpendicular to the magnetic field or the coil itself is in a horizontal position, the induced EMF will be at a maximum. And we can clearly see it at a maximum in the graph. Let's continue rotating the coil. We will see that now the coil is in a vertical position. If we draw normal to the area of the coil, it is parallel to the magnetic field. So when the coil is either in a vertical position, we can look at it from one orientation. And if we look at the area of that coil, we can see that the area is parallel to the magnetic field. In this orientation, the induced EMF is at a minimum. And we can see that graph comes and cuts at the x-axis. If we read off the voltage, it's 0 volts. So if we consider AC and DC generators, and we know that they're used in industry, there must be ways of improving the efficiency of these generators. And so there we have a generator. How do we know that it's a generator? Because we've got a coil rotating in a magnetic field and an EMF is induced. So we can improve its efficiency by increasing the rate of change of magnetic flux. What does that mean? We can rotate the coil faster. We could also increase the magnetic field strength by using stronger magnets. We can increase the efficiency by increasing the number of turns on the coil. And if we increase the area of the loop, that would also increase the efficiency of the generator. So let's consider how are generators used in daily lives or in industry. And let's consider the uses of AC generators. Of course, AC generators are used to generate electricity. So there's our power station, and that's our site of generating large amounts of electricity. At construction sites or on construction sites, I don't know about you, but I haven't seen electrical sockets and cords all over on construction sites because it would be quite dangerous. So they use AC generators. Why? Because we don't need an electrical input. Through mechanical energy, that is being converted to electrical energy, and these AC generators thus provide a source of electricity on construction sites. The fun fair. If we look at our fun fairs and those massive rides, surely we need electricity to power those rides for us to go and have fun on. And again, we use AC generators to generate electricity which powers these rides in fun fairs. We use bicycle dynamos, that's an example of an AC generator, and of course they're used in cars as well. That's a little load shedding schedule over there, and so you know that many people, if they can afford an AC generator, they use generators during power outages to provide electricity for their household or even their businesses. Most of our household appliances use electricity generated from AC generators to power them. There we have a blender and even a coffee grinder. So let's look at the uses of DC generators. Electroplating factories make use of DC generators. Again, there's a link between this part 1 and part 2 of electrochemistry. In electrochemistry, we looked at how electrolytic cells are used in industry, and we considered electroplating. So if we look at that image over there, we've got a very tarnished ring, and it's being electroplated, and now it's gone back to its gold state. So it's not a golden ring, it's a metal with less value being plated with gold to look like this. So electroplating factories make use of DC generators to run those electrolytic reactions. Older vehicles also use DC generators to charge batteries, and some locomotives and ships would also use DC generators for power. And then low voltage and low current appliances use DC generators. So right, grade 12s, we are now in a position where we have covered both AC and DC generators. So let's go see how they are assessed in a test or an exam. So let's work through the application section. We will look at paper 1, November 2019, question 9.1. So it reads, a simplified diagram of an electric generator. So now we know we're looking at our generator section of electrodynamics, is shown below. When the coil is rotated, that's also another sign that we're dealing with a generator, and EMF is induced. Remember those criteria that we spoke about? We need a coil to rotate in a magnetic field, and we know that an EMF will be induced. There's our diagram, there's our magnetic field. So even though they never said or mentioned the magnetic field in the blurb above, they do show that in the diagram. So we have all the checks to know that an EMF will be induced. Question 9.1, it says, is this an AC generator or a DC generator? Grade 12s. We've covered how to figure out if it's AC or DC. They've told us that it's a generator, and we now need to decide. And the deciding component of an AC or DC generator is whether we have 2 slip rings or whether we have 1 split ring commutator. And it is quite clear. Over there we can see that little hamburger roll without the patty. We can see we have a split ring commutator, and that's indicative of a DC generator. That gets you 1 mark. Let's continue. 9.1.2. Briefly explain how an EMF is generated in the coil when the coil is rotated by referring to the principle of electromagnetic induction. So if you still weren't convinced that we were working on generators, you know that we are, because generators are based on the principle of electromagnetic induction. So we know that there is a change in magnetic flux linkage, or linked between the coil or armature as it, or let's say between the coil and the magnetic field, as the coil is rotated. And this induces an EMF. It's always a good thing to check, have you covered all the criteria to induce an EMF? And we spoke about magnetic flux linkage between the coil and the magnetic field as it is rotated. All those are covered, and so we have now just explained how the electromagnetic induction is used as a principle for generators. 9.1.3, it says draw a sketch graph of the output voltage versus time for this generator and show one complete cycle. Now, grade 12s, you should know, I'm quite passionate about graphs, and you need to remember that there are two types, either a sketch graph or an accurate graph. A hint here, it's worth 2 marks, so it is definitely not an accurate graph. Another hint, they haven't provided you with graph paper. So please don't spend 20 minutes drawing this graph. It's 2 marks, it's a sketch graph. So all we want to do is use our ruler to draw the y-axis and our x-axis. Our independent variable is time in seconds, and our y-axis is output voltage. And remember, you tell us what's measured, and you always give the units. We now set for a sketch graph because all we're interested in is the shape of the graph. So now we know that we've got a DC generator. Why? Because we've got a split ring commutator. So we know that the current direction does not change for a revolution. So we know that it will always stay above the x-axis in this case, and so we know it will go to a maximum, and we'll have another maximum. And that's our graph. So let's have a look at another question which covers generators. We'll look at paper 1, November 2018, question 10.1. It reads, in the simplified AC generator below, the coil is rotated clockwise. 10.1.1, in which direction does the induced current flow in the coil? And you can choose only from X to Y or Y to X. So let's have a look at some key points in this question. We are busy with generators, and more specifically AC generators. And we know that the coil is rotated in a clockwise direction. And we need to determine the direction of the induced current, and we know that generators, we generate the right answer. We're going to use Fleming's right-hand rule to determine the direction of the induced current. But we need to describe it either from X to Y or Y to X. So your answer can't say clockwise or anti-clockwise or from positive to negative, anything like that. They tell you in which notation or which notation you need to employ to describe the direction of the EMF induced. All right, so we know that we need to determine the direction of the induced EMF, and because we have a generator, we're going to use Fleming's right-hand rule. Father for force, mother magnetic field, and child for current. All right, so here we start. If we look at our diagram, our magnetic field is going from north to south, so we're pointing that way. If we look at the arm XY or YX, if that arm rotates, so if this is XY, if it rotates, look what XY is going to do. It's going to go up. So my thumb needs to point upwards. So while I keep the direction of the magnetic field from north to south, as in the diagram, XY will be rotated upwards, and child is pointing towards me. Okay? It's pointing towards me. North to south, XY, the coil section, is moving upwards, and my induced current is pointing towards me. So if I look at that in relation to XY or YX, the induced current is coming towards me, which means it's moving from Y to X, and that's my direction. So 10.1, the direction of the induced current is from Y to X, and that's all we write. 10.1.2, on which principle is the working of the generator based? It's Faraday's law of electromagnetic induction. Isn't it beautiful when you can see how all the theory and all the rules, all that work that you think, do I need to study it? Yes, you do, because they actually ask you these questions in the exam. And I mean, we already scored 2 marks, and that was purely based on theory. We haven't even started application of equations or anything like that. Last question, 10.1.3. State the energy conversion that takes place while the generator is in operation. We know that for a generator, mechanical energy is converted to electrical energy. And to confirm the mechanical energy, we are rotating the coil in a magnetic field, and an induced EMF is generated. So we've got mechanical energy converted to an electrical energy, and this is indicative of a generator. So grade 12, we've covered 2 applications. In both exam questions, we have seen how all the theory based on AC and DC generators can be asked in an exam question. I do encourage you to work through your Boost Prep Pack and tackle more questions that cover the topic of AC and DC generators in the section of electrical machines for electrodynamics. I look forward to seeing you in part 2 of electrodynamics, where we will be looking at AC and DC motors.